Hello, my dear students. This is Ratnam from Government Degree College, Bodhan. Today, I am continuing my session. This is in continuation with the previous session of chemical bonding for first year BSc students. This is the third part of chemical bonding. In the last session, we were discussing about molecular orbital energy diagram. How do we write that? And we have taken two examples. That is hydrogen molecule and another is nitrogen molecule N2. And we explained that hydrogen molecule is having what bond order 1 and how a molecule is formed. That is this two atomic orbitals of hydrogen, how they combine to give antibonding and bonding orbitals, and how to calculate bond order, and also whether is it a paramagnetic or diamagnetic, how to decide that. And also we explained whether the molecule is stable or not. So these are the three important features we can explain by using molecular orbital energy diagram. So we have completed these two molecules, that is hydrogen and nitrogen. Now let us continue our molecular orbital energy diagrams of different molecules. Now let us take oxygen. Now look at the molecule oxygen. In oxygen, oxygen is 8, atomic number is 8. So the configuration 1s2, 2s2, 2p4. So in this altogether 8 plus 8, total number of electrons involving in O2 molecule is 8 plus 8, 16. So total number of molecules is 16. You can look at the diagram totally. In the last bottom one, it is 1s interaction. So the molecular orbitals are totally filled, and above that 2s interaction, again molecular orbitals are totally filled. And on the top of the diagram, if you look at the top of the diagram, they here on the left side 2p4, right side 2p4. That means left side one oxygen, right side another oxygen. Now when they interact with each other, the total number of electrons are 4 plus 4, 8. Now out of these 8 electrons, if you look at the diagram, the sigma orbital, bonding sigma orbital is on the bottom, and pi bonding orbitals, that is py, px, both are on the upper side. And if you look at the again upper portion, pi star 2py, pi star 2px, both are having what upper energy level, and above that sigma star 2pz. That is pz interaction is a sigma type of bonding, whereas py, px are interacting like partial, that is sideways, it is nothing but pi bonding. When we are filling 8 electrons in the topmost 2p interaction, when we are filling 8 electrons, then we are filling 6 electrons on the bottom side, that is on the bonding orbitals, and there are 2 electrons which are remaining there, and they are filled into the pi star 2py, pi star 2px. So one electron in 2py, another electron in pi star 2px. So we can clearly see that the total number of unpaired electrons present here are 2. Total number of unpaired present are 2. So what does it mean? Simply, already we had a discussion on that, that whenever we find unpaired electrons in the energy diagram, that indicates that it is a paramagnetic in nature. So these 2 electrons are unpaired electrons, therefore it gives paramagnetic nature to O2 molecule. Now what is bond order? Already you know that bond order is calculated based on the formula. The formula is number of bonding electrons minus number of antibonding electrons by 2, that you know. So bonding electrons you can just calculate 2 plus 2 plus 6, that is 10, and antibonding electrons 2 plus 2 plus 2, that is 6. So 10 minus 6. So altogether 10 bonding electrons, 6 antibonding electrons. So the difference is 4. 4 by 2. 4 by 2 is give nothing but 2. The bond order is 2. So oxygen bond order is 2. That means oxygen is having double bond with respect to other oxygen. Now, the nature of oxygen is paramagnetic because of the presence of two unpaired electrons, and it is a stable molecule. We already know that whenever the bond order is a positive value, it gives stable molecule. Now, let us take another example. Yeah, O2 minus 2. It is given. You see, this is the total what different oxygen molecules, where we can write O2, O2 plus, O2 minus, O2 minus 2. Now, what is the difference? How can we write all this at a time? Very simple. It is very simple to understand here. Look at the total number of electrons. O2 means 8 plus 8, 16. If you take O2 plus, so remove one electron, then it becomes 15 only. You can look at the diagrams in the how electrons are filled in the energy levels. You just look at this. First in O2, total 16 electrons are there. Therefore, on the upper side, that is pi star 2p pi star 2p is there now. So in that, two single electrons are there. But when you take O2 plus, then one electron is less. So the total number of electrons is 15 only. Therefore, what happens? One electron is missing there. So total number of unpaired electrons are 1, and bond order also is reduced. Similarly, if you take O2 minus, then O2 minus means one electron is extra added. So once one electron is extra, then that extra electron will go and combine with the pi star only with a single electron. Therefore, again number of electrons are only 1. Unpaired electrons are 1. But the bond order will change. O2 minus will be having bond order 1.5 because in anti-bonding number of electrons are increasing. So the only difference is anti-bonding number of electrons are increasing. In our syllabus, O2 minus 2 is given. Now O2 minus 2, when you look at the O2 minus 2, what is the total number of electrons? Oxygen 8, another oxygen 8, 16. To this minus 2 means 2 electrons are extra added. So altogether 18 electrons. So when it is coming to be 18 in number, 18 electrons, out of 18 electrons, how many are bonding or how many are anti-bonding? You see that there are 2 extra electrons when compared to O2, and that 2 electrons are already paired up at pi star only. They are paired up at pi star only. You can see the diagram, the last diagram. You see that the upper part, pi star 2p. In that, two electrons are written. That means all electrons are paired up. There is no unpaired electron. Therefore, O2 minus 2 total number of electrons are 18, and the bond order is 8, 10 minus 8, that is 2 by 2. 2 by 2 means 1. So the bond order is 1. So if you take O2, the bond order is 2, whereas if you take O2 minus 2, the bond order is 1. And is there any unpaired electron there? No, there is no unpaired electron. Therefore, it is diamagnetic in nature, and already we know that it is a positive bond order means a stable molecule. So O2 minus 2 is a stable molecule. Now, another molecule F2, that is fluorine. Fluorine. You know, fluorine is a halogen, where you can look at the configuration, electron configuration. 1s2, 2s2, and 2p5. So 5 plus 4 altogether 9 electrons. So F2 molecule means 9 plus 9. Total is 18 electrons. So when the total number of electrons is 18, then we can expect same diagram. Just we had seen O2 minus 2, because O2 minus 2 total number of electrons are 18. For F2 also total number of electrons are 18. Then filling up, when you fill up the molecular orbitals, definitely 18 means they end up similarly. So the bond order should be also same. Magnetic behavior must be same. Stability must be same. So the electronic arrangement, bond order, and magnetic behavior are almost similar when we compare O2 minus 2 and F2. Same you can see in the diagram also. F2, 1s interaction, 2s interaction, and 2p interaction. When the interesting part is 2p interaction, when you look at the upper part of the molecular orbital diagram, 2p interaction. Left side 2p has 5 electrons, right side 2p has 5 electrons, altogether 10 electrons. In that, total 3 plus 3 orbitals are 6. So out of 6 atomic orbitals, we get 3 bonding orbitals called sigma 2p, pi 2p, pi 2p, and again 3 anti-bonding, pi star, sigma star. And the total number of electrons are 10. 10 means first these 3 bonding orbitals are completely filled, and in anti-bonding pi star again 4 electrons are completely filled. Therefore sigma star is empty. We don't have any electron there in sigma star. So altogether 10 electrons are completely filled. Now when you calculate the bond order, same way just like we have calculated for O2 minus 2, here also total number of bonding electrons are 6 plus 2 plus 2, that is 10, and anti-bonding are 2 plus 2 plus 4, that is 8. 10 minus 8, that is nothing but 2. It comes out to be 2 by 2. 2 by 2 gives 1. So the bond order is 1. We know that F2 bond order is F is what having single bond with another fluorine atom. So F dash F we generally represent like F dash F. So this is diamagnetic in nature because it doesn't have any unpaired electrons there. Therefore, it is diamagnetic. It won't show any paramagnetism. And bond order is 1. So it has having stability also. The molecule is quite stable. We know that F2 does exist. Very clearly, it exists. Now, up to now, we had discussions of same type of dimers, that is mononuclear. We have taken F2, H2, N2, so like that. That means same atom combining with the same type of atom. Now, from here onwards, we will be taking molecules with heteroatoms. That means one atom combining with another type of atom, like carbon combining with oxygen. So in such cases, what happens? How do we consider this MOED, that is molecular orbital energy diagrams? How to represent this? Now, when you write such cases, then you have to understand one factor, important factor, that the energy levels will not be same. The diagram will not be symmetric. Why? Because one is one. Both are different atoms. So when both are different atoms, naturally we can't expect the energy levels to be same. Therefore, the diagram is also little bit distorted. Looks like distorted. So this is the case in so many other combinations also. Depending on the difference in the energy, the distortion takes place. Okay. Now here you see here carbon monoxide CO. Now already you know the combinations of carbon and oxygen. Carbon electron configuration is 6 1s2 2s2 2p2, and oxygen is 1s2 2s2 2p4. So oxygen is for carbon and oxygen. 1s is same for both 2 electrons, and 2s is also same 2 electrons. But if you look at 2p levels, then carbon is having only 2 electrons at 2p level, whereas oxygen is having 4 electrons at 2p level. So the difference, whatever is there, is based on the 2p levels only. So 1s interaction is same. Just already we know that 2s interaction is also same almost, because in 2s interaction only bonding, anti-bonding both are completely filled. Now when you look at 2p interactions, they are quite interesting there. 2p interactions are little bit interesting. They look like here. You see the diagrams. 2s red lines are given. Red color lines are shown for 2s interaction. They are quite different there. The diagrams are little bit mixed up here. And look at the 2p interaction. In 2p interaction, altogether 2 electrons from carbon and 4 electrons from oxygen combined. The total number of electrons are 4 plus 2, 6. So when you take 6 electrons, all 6 electrons are filled completely into bonding molecular orbitals, because we know that there are 3 bonding molecular orbitals between 2p interaction. 2p interaction gives 3 bonding molecular orbitals and 3 antibonding. But the total number of electrons are 6 only. Therefore, 3 bonding molecular orbitals are completely uh, filled. Now, antibonding molecular orbitals of 2p will not be having any, are empty. That is pi star, and sigma star are empty. So, total number of bonding electrons, how many? 6 plus 2 plus 2, that is 10. And antibonding, 2 plus 2, only 4, because 2p doesn't have any antibonding electrons. Therefore, 4. 10 minus 4 is the bonding minus antibonding. So, 10 minus 4 means 6. 6 by 2. 6 by 2 means 3. So, the bond order is 3. Total number of electrons, E number, I have given electron number is 14. And 10 minus 4 gives 6 by 2, that is nothing but 3. So the bond order is C. Carbon monoxide has the bond order as 3. And is there any unpaired electron? No, it doesn't have any unpaired electron. Therefore, it is diamagnetic in nature, and it is quite stable. It is clearly known. Now, this is another molecule, NO. This is nitrogen combination with oxygen. Again, hetero combination. One is nitrogen, another is oxygen. Nitric oxide, we can call it as. Nitrogen configuration is 7, oxygen configuration is 8. So 7 plus 8, 15. Total number of electrons are 15, already I have mentioned there. And out of 15, how do we write? That we know that almost here the energy diagrams are little bit closer, not that far away. Just now carbon and oxygen, here nitrogen, oxygen are nearly having same energy levels, but still there is some gap. You can see 2s interaction is little bit up and down. You can see this nitrogen is at a higher level, oxygen is at lower level, 2s. Similarly, 2p also little bit difference. The difference here is in 2p, nitrogen is having 3 electrons, whereas in oxygen it is 4. That means left side 3 electrons, right side 4 electrons. So total is 7. So out of 7, 3 bonding molecular orbitals are completely filled by 6 electrons. So there is 1 electron remaining, which is occupying into pi star. Okay, that is antibonding molecular orbital. So in antibonding molecular orbital, there is 1 unpaired electron. Now we can calculate the features. How can I explain that? First, bond order. The bond order is total number of bonding molecular orbital electrons are 10, minus antibonding means 2 plus 2 plus 1, that is 5. 10 minus 5, it is 5. So 5 by 2 is 2.5. So bond order is not exact 2 or 3, it is in between 2.5. Now unpaired electrons, yes, there is 1 unpaired electron, very clearly we can see, and pi star. Therefore, it is paramagnetic in nature. And of course, it is a stable molecule because um, already I told you that any positive value leads to stability. But bond order is 2.5. That is half. The bond order is not completely 3, neither it is 3 or 2. So this is what we understand. And regarding with NO is the diatomic molecule. Now you can see this NO plus, same, but we are getting positive charge again. So once the positive charge is taken, means total number of electrons become, NO means 7 plus 8, 15. Just plus charge means 1 electron is removed. Therefore, the number of electrons becomes 14. Isn't it? 14 electrons means again the model of filling the orbitals. Similarly, there will not be, that last electron will not be here. You look at the diagrams, you just compare. You won't see that pi star electron here. That is, pi star electron is missing here because it is NO plus. Therefore, what happens? Antibonding electrons becomes, 1 electron becomes less. So that is, in previous case it is 5. Antibonding electrons are 5, whereas here the antibonding electrons are 4. The filling up of the electrons is same. Electron filling is same, similar. So total number of electrons are 14. When you calculate bond order, the number of molecular orbitals, bonding molecular orbitals, electrons completely filled is 10, minus antibonding electrons are 4 only. So 10 minus 4, it is 6. and 6 by 2 gives 3 as a bond order. NO plus is 3 bond order. But number of any unpaired electron is there? No, you won't find any unpaired electron. Therefore, it is diamagnetic in nature. So this is how we calculate NO plus. So a slight difference. So once you understand NO, and you can easily write NO plus, because the only difference is in NO there is one electron, extra electron in pi star, and NO plus means that electron is no more there. Therefore, the total number of electrons are 14, and that single electron is missing. Therefore, bond order increases and also magnetic behavior changes. Now, this is a cyanide Cn minus. You already know that carbon 6 electrons, nitrogen is 7 electrons, altogether 6 plus 7, 13. Minus means 1 extra electron. So 6 plus 7 plus 1, total is 14 electrons. So total number of electrons are 14. So when the electron number is same, it must be similar to NO plus, isn't it? Electron numbers are once is decided, then the diagram shape will be almost more or less same. So 14 means we can easily calculate the bond order and magnetic behavior of the molecule. So cyanide minus, you see that um, it is same carbon with 2 electrons in 2p level, and nitrogen in 2p level it is actually having 3 electrons, but one minus, due to minus charge it is showing 4 electrons there. Therefore, altogether 4 plus 2, 6 electrons in 2p level. So when you fill up that 6 electrons, then 3 bonding molecular orbitals are completely filled by 2, 2, 2, 6 electrons totally, and anti-bonding molecular orbitals, that is pi star, sigma star, are empty. Therefore, bonding electrons, how many bonding electrons are all together? 1s2, 2s2, and 2p6. So altogether 2 plus 2 plus 6, 10. And anti-bonding are only 2 plus 2, 4. Therefore 10 minus 4, that gives 6. And 6 by 2 means 3 is the bond order. So it is almost same bond order when compared to previous example. And is there any unpaired electron here? No, we don't find any unpaired electron here, because in the diagram it is clearly showing that we don't find any unpaired electron. Therefore, it is diamagnetic in nature. Now we have come to the last part of this MOED diagrams. This is hydrogen fluoride. Hydrogen fluoride is an acid. It is very typical example, you can say, because such diagrams are very difficult to write, because already in the previous session, when in the beginning of molecular orbital theory, we explained that there is a condition for what LCO, linear combination of atomic orbitals. That what is the condition means? Energy levels of the two atomic orbitals must be nearly equal. That must be nearly equal. To some extent, they must be equal. Otherwise, what happens? The combination will not be to that extently possible. So here, this is a typical example where the energy levels of hydrogen and fluoride are quite different. What is the actual interacting factors here? You look at this. Hydrogen, what is the electron configuration? Hydrogen is 1s1. Whereas fluorine is 1s2, 2s2, 2p5. So there is 9 electrons, fluorine. Hydrogen is only 1 electron. So altogether 10 electrons. But out of 10, will it be possible to have total molecular orbitals? No. All molecular orbitals are not possible here. Here 1s means hydrogen interacts with only one atomic orbital of fluorine. What is that? That is 2p. In fluorine, you look at the electron configuration of fluorine. In the last part of electronic configuration of fluorine, 1s2, 2s2, 2p5. 2p5 means again in the 2p levels, the last orbital is having one electron. So that single electron carrying p orbital and 1s orbital of hydrogen both interact or both combine to give molecular orbitals, only two molecular orbitals, and all remaining are non-bonding molecular orbitals. You can call it a non-bonding molecular orbitals, because 2px, 2py non-bonding molecular orbitals, and 2s non-bonding, 1s also non-bonding in fluorine, whereas 1s of hydrogen, 2pz of fluorine only combine. Okay, so the interaction is between 1s orbital of hydrogen, 2p orbital of fluorine. On the right side I have clearly mentioned. So that interaction is only specific interaction taking place here. Therefore, the diagram you can see here in the diagram, yeah, 1s orbital and 2p orbital of fluorine, they are interacting, and we expect two molecular orbitals, only two molecular orbitals. One is bonding, another is anti-bonding, and total number of electrons, how many? From hydrogen in 1s there is one electron. In fluorine, in the p orbital of fluorine, there is only one electron. So total number of electrons are two, only two electrons. Therefore, the two electrons are filled in the bonding molecular orbital, and the sigma star anti-bonding molecular orbital is empty. So when you write the bond order, what is the number of bonding electrons means two only. What is the number of anti-bonding electrons? Zero. So 2 minus 0, the total answer is 2. And 2 by 2, the answer is 1. Therefore, what is the bond order? Only 1. 1 is the bond order. So you need not consider total number of electrons in fluorine. Fluorine has 9 electrons, but should not consider all that. You have to consider only 1 electron from fluorine and 1 electron from hydrogen. So altogether total number of electrons are 2 only in this particular case. And all the remaining are in non-bonding position. They are not considered to be in bonding position. Okay, so the bond order is 1. And is there any unpaired electrons here? No, not at all, because whatever the unpaired electron is totally paired up right now. Therefore, it is diamagnetic in nature. And as the bond order is not zero or negative, therefore it is a stable molecule. So this is what molecular orbital diagram to understand hydrogen fluoride. So these are all different examples. We have covered almost according to the syllabus given in the first year BSc unit 1, chemical bonding. So molecular orbital energy diagrams, different diatomic with homonuclear diatomic molecules, and also we have covered heteronuclear diatomic molecules with different shapes and diagrams. We are covering in every molecular orbital energy diagram. We have shown how to calculate bond order and how to decide number of unpaired electrons, and based on that whether the molecule is a paramagnetic or diamagnetic. And after that we also covered whether the molecule is stable or not. Based on the bond order we can say it is a stable or not. So this is the completion of the unit 1 first topic, that is chemical bonding. Thank you from my side. This is Ratnam, Associate Professor of Chemistry from Government Degree College, Bodhan. So this lesson is completed. The next session we will take up another lesson. Thank you very much.